All right, it's 11 o'clock, so we'll go ahead and get started. And hopefully, some others will join us soon. Remind you again, our next test is Tuesday after we come back from our break at 11 o'clock, and we'll go up through section 5.5, which we're going to finish here today. That's what we'll spend most of today on. We might have time to talk a little bit about what's coming up in chapter 6. We'll see. But let's go ahead and get started talking about these statically indeterminate problems that we're hopefully going to learn how to solve today. Uh, this I'll remind you in your textbook, as in section 5.5. And what we're looking at is trying to figure out how do we solve a problem maybe similar to this. We'll call this A and C. And so if we apply a torque to a shaft like this, excuse me, again, still we're only looking at shafts with circular cross section. But you see, this is fixed at each end. And so we're going to have some torque, we'll call it TA, and some torque TB. But how much torque section AC actually carries and how much torque is in section BC depends on the length of each section, the material each section is made out of, and the size, the cross-sectional area, the polar moment of inertia, all have an effect on how much torque each side would carry. We can't just say, well, this is going to be half and this is going to be half. That would only be true if it was perfectly symmetric. But we want to look just in general, how do we determine if it's not perfectly symmetric, how much torque is in this part of the shaft and how much torque is in the other part of the shaft. And we talked about it's going to require both equilibrium and what we know about deformation. So yesterday, we talked about equilibrium means the sum of all these torques got to be equal to 0. So TA and TB have to add up to be equal to T, but they don't have to be equal. The sum of those has to be equal to T, or you add them all together like this is equal to 0. Right? And that's where we get one equation from. It's from equilibrium that the sum of torques be equal to 0. So that's basically, I think, where we stopped yesterday. So now let's talk about deformation. What we know about deformation and how we can use this. And in the book, if you read through this, you'll see he refers to this as compatibility condition. All right, so let's go back up here to our picture, and let's look at this part of the shaft. If you can imagine if we cut it there, right in, may not be right in the center, but let's see where this torque is applied. And if you look at the left side, this part of the shaft AC, then I know the angle of twist here at this cross section C has got to be equal to however much this part of the shaft AC rotates. So it'd be the angle of twist of C with respect to A. If we want to be, I reckon, complete plus whatever the angle of twist at end A is. But if this is fixed, A doesn't twist, it doesn't rotate, it's fixed. So what I've got then is the angle of twist at C has got to be equal to whatever the angle of twist of the section AC is. But we also, right, can do the same thing if we look at the right side of the shaft. And I know the angle of twist there at C has got to be equal to however much the section BC twists. So the angle of twist of C with respect to B, plus whatever angle of twist there at B, but just like above here, if B is fixed, it doesn't rotate. And so that's 0. So we get the angle of twist at C has got to be equal to the angle of twist of C with respect to B. So however much this part of the shaft twists, that's got to be what the angle is at C. Well, if the angle of twist at C is equal to this, and it's equal to that, right, then we know those two things, right, must be equal also. And so this is where we get our, what the book calls a compatibility condition, is the angle of twist of C with respect to A, it's got to be equal to the angle of twist of C with respect to B. Right. This is where we're going to get our second equation from, right? Because in the previous section, we talked about how to calculate angle of twist, right? This angle of twist would be TL over JG for section AC. Got to be equal to TL over JG for section BC. Right? And that's where we're going to get equation 2. So then we'll have two equations, two unknowns, and we can solve for those torques. If you think about it, this really is, it kind of formally went through this, but I suspect most of you would buy this, even without some kind of formal, I don't know if I call that a derivation or not, but basically what this says is the cross section here at C, where these two sections meet, have to rotate the same amount. That's all this is. And if you think about it, that's got to be true. The only way that would not be true is if the thing broke, right? If the thing actually broke at C, is the only way one part of that could twist more than the other. Otherwise, they got to twist the same. Right? I don't know how this will show up or not, but right. So we'll do a little demo here with my fingers. Right. So pretend like my fingers are the shaft up here. Where my fingers meet is at the cross section there at C. Right. So here where these my two fingertips meet is C. All right. Well, all this says is if this rotates, that point where they meet has to rotate the same. Right? The only way that would not be true, right, if one rotated more than the other, right, the material would have to fail and break. That's the only way they could not rotate the same amount. And that's all it says. And that's where we get our second relationship from, and what we know about angle of twist being equal to TL over JG. That's going to give me a second equation with those two unknown torques in there. And that's basically the pattern, the process, procedure we're going to follow for all of these statically indeterminate problems. All right, so before we work a problem, any question about this concept or idea about, again, what the author calls compatibility condition? All right. Pretty good conceptually. Then let's see if we can put some numbers in here and go through and work a problem. All right, so let me draw this. And we're asked to find the maximum shear stress section AC and BC. So what we're going to have is a problem similar to what we were just looking at. We've got this part of the shaft is longer than this side. And this part is aluminum. And over here is, it's going to be, see if I can write steel in here. Yeah, you can see that. This aluminum part, AC, is 6 feet long. And the steel part, which my picture's not to scale again, is only 3 feet long. We're told the aluminum has a 3-inch diameter, and the steel is smaller, and again, not to scale, but it says 2-inch diameter. And we're also given the modulus of rigidity for the aluminum is 4 times 10 to the 6 psi. And G for the steel is 12 times 10 to the 6 psi. And we're going to apply a torque here at C of 10 kip inches. All right, so our shaft is, again, it's composite. Part of it's aluminum, part of it's steel. It's fixed at each end. We're going to apply this torque out there somewhere in the middle. And our goal is to determine what's the maximum shear stress in this aluminum section AC, and what is the maximum shear stress in the steel section over there, BC. So to get the maximum shear stress, we need to know what the torque is in this aluminum part, and we need to know what the torque is in the steel part, because we can't just look at it and say, well, this is going to be 5 and that's going to be 5. It doesn't work that way, because you see the steel is like 3 times as strong as the aluminum. The aluminum, though, part is bigger than the steel, so that's going to compensate or offset that somewhat. Plus, you got different lengths in there, so we're going to have to go through the process that we just talked about to determine what is going to be the torque in the aluminum and what's going to be the torque in the steel part. And essentially, this is, before we get started working here, we basically did similar problem when we were doing statically indeterminate axially loaded members, right? I don't know if you remember or not, but we did a problem earlier where we had a concrete column, had a steel I-beam down the middle of it. And again, this has nothing to do, it's just extra information. I'm digressing a little bit here, so. But if you recall, we had this problem. We had this column, and we had this steel I-beam. My picture's bad, but get the idea. And we had some force. And, you know, if you cut it and you look at the free body diagram, you know, we had the force in the steel. Let me draw a new picture. Scratch that. Try again. So we had the force in the steel and the force in the concrete. And I forget what this force was, but when we worked this problem, right, we couldn't just say, well, half's going to be in the steel and half's going to be in the concrete. It doesn't work that way because you got the different materials, you got different sizes, and we had to use equilibrium and deformation to determine what those forces were. This is essentially the rotational equivalent of this same problem. Okay? Instead of an axial force, we got a torque. We got a moment applied, but it's the same concept. We got to use equilibrium and deformation to figure out what torque is going to be in the aluminum and what torque is going to be in the steel. Right? Anyway, I digress, but so if our applied torque is this way, we're going to have, just draw basically my free body diagram here on the picture. Right? This is what we got to try to find. What's what I call TA and TB. Because TA is going to be the torque that's in the aluminum part of the shaft, AC. TB would be the torque that's in the steel part of the shaft, BC. But I know from equilibrium, right, some of the torque got to be zero. We got to define one way positive. We'll go this way as positive. So TA plus TB, they're going in the positive direction. The 10's going in the negative direction. It's got to add to zero. All right, so I've got this equation from equilibrium and the fact that I know the torque's out to zero. That's all we get from equilibrium. Right? Some of the forces, setting those equal to zero doesn't tell us anything because we don't have any forces. Right? So now we go to what we know about deformation, or if you want to refer to it as the compatibility condition. I know this point C here, right, where they meet, I know the angle of twist of C with respect to A has got to be equal to the angle of twist of C with respect to B. This cross-section C, where those two sections meet, has got to rotate the same amount. And I know from that then that TL over JG for section AC has got to be equal to TL over JG for section BC. Well, the torque in section AC is what I call TA. So this is TA. The length is 6 feet. Now, well, I'm going to go ahead and I'm going to convert that to inches because I know J down here I'm going to do in inches, but I'll come back and ask a question related to this in a minute. So it's 6 feet long. If you wanted to convert that to inches, you multiply by 12. J, remember J for a circular cross section, pi over 2 c to the fourth, right? C being the radius. And we have a 3-inch diameter. So J here would be pi over 2. The diameter is 3, the radius is 1.5. So it'll be 1.5 inches to the fourth. That would be J. G, this section AC is of the aluminum. And this is 4 times 10 to the 6th. This is PSI. Again, if you want to make sure everything's compatible, notice the 10 here, this is in kips. So if you want to be safe, we convert that to KSI. So 4 times 10 to the 6th PSI is 4 times 10 to the 3rd KSI. Right? Then we do the same thing on the right side. here, the torque in BC is going to be, I call that TB. The length is 3 feet. Since we did it over here, we got to do it over here. Multiply by 12 to get inches. J, same thing, pi over 2. The radius to the fourth here, it's a 2-inch diameter. The radius is 1 inch. And again, we converted this to KSI. This has got to be KSI. So 12 times 10 to the third KSI. And now, before I go any further, just an observation. Yeah, I multiplied by 12 here, right, to get inches. But technically, that wasn't not necessary. All right, hang on just a second. I'll answer a question that I just see popped up. But let me finish this first. But it's really not necessary. We could have left this in feet. If we leave this in feet, as long as the units are the same, they're going to cancel anyway. So if we have 6 feet here and 3 feet there, we're going to get the same thing. If we multiply both sides by 12, it's not going to change our answer. Same thing we did down here. When I multiplied or changed this to 10 to the third to get KSI, that was not necessary. We could have left this in PSI. As long as both of them are in PSI, the units cancel, and it's not going to affect your answer. So just wanted to point that out. If you were sitting there thinking, well, do we have to multiply by 12 and get the length in inches? No, we could have left this in feet. As long as they're both in the same units, you're okay. Same thing for G. So the question asked was, would we solve a square cross-section be as simple as changing J? No. Not anywhere close. If you're twisting a shaft with a square rectangular cross-section, this formula is useless. Doesn't work. This formula, the TL over JG, is only valid for a circular cross-section. If it's not circular, that don't work. It's a totally different analysis that you'd have to do. That's why we don't do anything that's non-circular in mechanics of material. Okay? So anyway, crunch all those numbers out, and I got TA is equal to 1.185, or actually I got to solve for TB. It is 1.185 times TA. There's my second equation. So I've got this equation up here from equilibrium, involves TA and TB. And I got this equation down here, relates TA and TB. And so now it's just a matter of doing algebra. Take this, substitute in that equation. We'll skip some of the algebra. Just take those two equations, solving. I got TA to be 4.58. These are kip inches. And TB, 5.42. Yeah, that's right. 5.42 kip inches. So we see they did not each come out to be 5, right? Because you got different materials, different sizes. All that factors in and will determine, again, how much torque the aluminum takes compared to how much torque the steel is going to take. All right? So this is the new part of the problem, is solving this statically indeterminate problem and determining what those torques are. The final steps of the problem is not new, right? We've found shear stress before. Yeah. So that's not new. We've done that, but so I'll pause a second. Any question? This process that we just did define those two torques. All right. Well, then again, we know tau max is going to be in the outer surface. TC over J. Right? T is the torque. That's where we're going to use the torques we just found. C is the outer radius. J, same as it was up there. So to get maximum shear stress in AC, we're going to take torque we found here, TA, 4.58. C is the outer radius, so it's 3-inch diameter. That's 1.5 inch radius. J is the same as it was up here, pi over 2 c to the 4th. And we solve, and now it'll give me what the maximum shear stress is in the aluminum part of the shaft up here, AC. And I got 0.86 KSI. It's again our moments in kip inches, so this will be in kilopounds per square inch. And tau max for section BC, the steel part. I'm going to take the torque in the steel, which was 5.42. C here, the radius would be 1 inch. And J is pi over 2, 1 to the 4th. And I got, what was that? 3.45 KSI. Again, this part, nothing new. We've done that before. Any questions about this one? It's again, you're going to follow very similar, steps for all of these statically indeterminate problems. They're all going to be similar to this. It's where you've got the thing constrained at both ends, and you got different materials, different sizes. Any questions about this particular problem? All right. Speak up if you need another minute to finish writing anything down. All right. What I wanted to do last thing is not necessarily go through and work the whole problem out, but maybe we just kind of look at how we would set this up. If we had something kind of similar, but a little bit different than, see, the one we just did, in the fact that, again, we'll call this aluminum and this one's steel again. But this time, what if the torque was not applied where those two where the two meet? The one we just worked, right? Our torque was applied there at C. What if we say came over here to point D, right? And we applied our torque there. Right, but we're still going to have these reactions, TA and TB, where TA is going to be the torque in all of this part of the shaft, and TB is going to be the torque in this part of the shaft. But how we would get there, as far as compatibility, is a little bit different. That we would still, from equilibrium, I know TA plus TB minus T is 0. Right? That's where we would get one equation. But the compatibility here is a little bit different. That's why I wanted to look at it again, but I don't think it's necessary we go through the whole calculations or anything. Okay. Long focus, sorry. Yeah. All right, so now we're back. So here, what I know is the angle of twist here at D with respect to this end A has got to be equal to the angle of twist of D with respect to this end B. Again, this cross section here at D, it's got to rotate the same, whether you're looking at the left, everything to the left or everything to the right. Right there where they meet at D, that angle's got to be the same. But the little bit of difference here is when we go this angle on the left side here, D with respect to A, we have to break that up into two sections because this is not all, the previous problem when our torque was at C here, everything to the left was aluminum and it was the same size. Everything to the right was steel, was the same size. But here at D, everything to the left is not the same material or the same size. So here you would have to break that up and you would get the angle of twist of D with respect to C and add the angle of twist of C with respect to A, because the material changes and the size changes. Now we're here, everything to the right of D is the same. You just have one. And so over here you would have, when you're doing TL over JG, you would use, the T would be TA. Over here would be TB. And of course the length and material and J would change. You go from D to C and then go from C to A. Those would change. The torque would be the same. Right? And so that's where you would get, your second equation from. Right? You'd have two equations, two unknowns, and you would solve that. Right? Any question about why from D to A we had to split up into two different ones? Because J changes, L changes, and which one? I forget if I said G or J, but J and G both change. All right. So I'll write it. So here again, you'd have TL over JG for D with respect to C. Yeah. So this is D with respect to C. So this would be for CD, and then TL over JG for AC. And again, this would be TA. And over here, you'd have TL over JG. This would be for section VB. Again, this torque would be TB. Right? Any question how to set that one up, or we would have to do it a little bit differently than, say, that first one we worked? All right, well, let's look at one more what if. What if we had, I don't know if you encounter anyone, if I assign any that would require this or not, but it doesn't hurt to look at it. We'll call this A, B, C, D. And here we're going to apply two torques. We'll call it T1 and T2. And just in general, assume, these are different materials, different lengths, different sizes. But equilibrium doesn't care about that. Right? You're still going to have two reaction torques called TA and TD. Right? And again, equilibrium. I'll put it right here. All right. So equilibrium, the torque equals, sum of the torques equals 0. TA plus TD minus T1 minus T2 is 0. Right, we got one equation, two unknowns. But here it's going to be a little bit more complicated to get the relationship we need, because we also don't know what the torque is in this middle section. The torque in BC, again, don't know, right? And you're going to see that's going to show up. Right? If we look at, say we look here at B. I know the angle of twist, B with respect to A, right? So the angle of twist of this side has got to be equal to the angle of twist of B with respect to this end. And just like we did up here, to go from B to D, we're going to have to break it up into two sections, right? So here we're going to have the angle of twist of B with respect to C and C with respect to D. Here's where this is going to show up, right? So when you do the TL over JG, the torque here between B and C, I don't know what that is. And so that's our third unknown that we have. Not only, this is the torque that's in AB, this is the torque that's in CD. I don't know what the torque in BC is. And so here, again, you would get the torque in section A, this is, you'd use the torque in B. So you're going to get another equation that's three unknowns in it, because we're going to introduce this other unknown. So rather than like up here where we had two equations and two unknowns, now I got two equations and three unknowns. So I got to have another equation. So let's go to a different point. Let's go to C. I know the angle of twist of C with respect to A. It's got to equal the angle of twist C with respect to D. Right here at this cross section C, it's got to rotate the same for the left side and the right side where they meet. Well, here, the left side, we got to break it up into two pieces, right? To get from C to A, we go C to B, and then from B to A. And that's got to equal the angle of twist C with respect to D. And here again is where my other unknown torque is going to come into play. This would be TA, this again would use TD, and that's where I get my third equation. So this one, in order to solve it, you'd have to solve a system of three equations and three unknowns. A little bit more work than, say, the one we looked at right above that. And I don't remember, I don't think I signed any that require you to go through and do three equations, three unknowns. I just don't remember off the top of my head. So I reckon it's possible, but if I did assign one, this is how you would get there. Okay? Any question about how to get there for one like this? All right, so this is, again, this is the last thing you're responsible for our second test. So that Tuesday we come back from break, your test will go from, again, wherever the first test ended up to this point. All right, any questions about twisting statically indeterminate shafts? Again, only with a circular cross section. Okay, well, we got about 10 minutes, so I want to take the 10 minutes and just kind of talk a little bit about where we're headed next. We're not going to get into too many details, but um, we'll continue this tomorrow and when we come back from break. But for now, um, when we move to chapter 6, the first thing we've got to talk about are what we call shear moment diagrams. Which, whereas chapter 5 was all about twisting circular shafts, chapter 6 and chapter 7 have to do with beams. So we've looked at axially loaded members, shear stress in joints, torsion of circular shafts. Now we're going to move into analyzing beams. And probably one of the most important things that you can learn, and it's absolutely necessary and essential, if you're going to analyze a beam, you have to be able to construct a shear force diagram and a moment diagram for that beam and the loading that's applied to that beam. And so that's the first thing that is the topic in chapter 6. And we'll get into actually how to specifics of how to do this some tomorrow. But all this is, there's two graphs. I can spell this, right? So two graphs showing the internal shear force and bending moment acting along the entire length of the beam. We have actually done this before. This was one of the first things we did, sort of. Well, the first thing we did in this course, this semester, was we found what the internal loadings were, but it was just at one specific particular point. Here we're going to take this to the next level, and we want to know what the internal shear force and bending moment is down the entire length of the beam, not just at one specific point. Again, if you go back to, pretty sure it was section 1.2, right? We found internal loading. Right, so we had a problem, just maybe, for example, something simple here. We had a beam like this, simply supported. I got some force apply. And you were asked to find what were the internal loadings at some point, like C, right? And what we did was we used method of sections and cut it. Right? So at this pin support, you'd have support reactions over here at this roller. But we cut it, and we either looked at the left side or the right side. So just for illustration here, let's say we look at the left side. Right, we'd have our support reactions that we'd have to find by applying equilibrium equations to the whole beam. And if you cut it at C, the notation we used was N for normal, and then V for shear force, and M for our bending moment. Now, just looking at this, and this is an assumption we're going to make in just a second in general, but for this particular problem, if you sum the forces in the x direction, there are no other forces. AX would be 0. So this would be 0. And so NC here would also be 0. But the shear force would not be 0, and the bending moment would not be 0. Those would be the internal shear force and bending moment at that specific cross section. Okay. But in order to analyze a beam, you're going to see in the coming sections, to calculate the maximum normal stress, we need to know what the maximum bending moment is. If I do this, all I get is the moment at C. That's probably, in fact, I can tell you, and just looking at this picture, if it's the scale, that's not the maximum bending moment. It is going to occur somewhere else. But that's what this moment diagram will tell me, is what is the maximum bending moment. Same thing for shear force. We'll see in chapter 7, we're asked to calculate maximum shear stress in a beam. Well, to get the maximum shear stress, I need to know what the maximum shear force is. That's what we use this shear diagram for. I look at the diagram and I can identify what the maximum shear force is, and that's what I need to calculate the maximum shear stress. Right? So just kind of giving you why we're doing this, what the motivation, why do we want a graph showing the internal shear force and bending moment. The reason is that's how we're going to determine the maximum shear force and the maximum bending moment. It's from that diagram. Now, two last little things and we'll quit. One, we're going to assume for now, that we have no axial forces applied. So a force like F here that's perpendicular to the beam, that's fine. That's going to cause the beam to bend. But we're not going to have a force like that, and in addition to that, a force pulling on it longitudinally or axially. That, for now, no. So we're just bending this thing. We will get to, I think it's in chapter 8, where we combine bending and axial forces. But for now, we're just bending. The last thing is I want to talk about sign convention, because this is going to matter when we get to our formulas for normal stress and shear stress. They're going to be based on this sign convention for V and M. So again, if you cut this beam, we're going to assume that positive V goes down. I probably mentioned this back in chapter 1, that the reason I was assuming these directions was we were going to define those as being positive later. Now, I didn't. If you look at the free body diagram on the right here, if V goes down, there it goes up here. So that would be what we define the positive direction for the shear force. And if it goes the opposite direction, so if V goes up here, it would actually be negative. And on that one, it would go down. Right? So that's what we're going to define the positive direction for shear force. And for the moment, likewise, what I assumed up here was the positive direction. And likewise, the opposite would be the negative direction. This would be a negative moment. Yeah, one way it's real easy to remember what's the positive moment and negative moment is a positive moment causes a beam to bend like this. Right? It's concave up. A negative moment causes a beam to bend like that. It's concave down. So you remember, if you're up, you're happy and you're smiling. Negative, you're down, you're sad, you're frowning. So that's a good way to always remember what's a positive moment or a negative moment. No good analogy for the shear force. You just got to remember this is what we're defining to be positive directions for V and M. All right. All right. So that's all I want to talk about today. We'll continue the discussion on shear moment diagrams tomorrow. Maybe we'll try to even get to construct one tomorrow. All right. Any question at this point related to shear moment diagram? All right, then that's where we're stopping today. I'm about to stop recording. If you've got questions about something, as always, stick around. And I'll be glad to help you out and talk about anything you want to. Otherwise, we'll be back tomorrow.
All right. Thank you.
You're welcome. Have a good day.